Okay, hello and welcome to our session. My name is Dominik Dörr. I'm one of the co-founders of the company SIMUTENCE, and today I'm going to talk about advanced composites forming simulation using the Abaqus add-on SimuDrape. First of all, I'd like to give a short insight into who we are actually. So we are focusing on the advanced virtual design with fiber reinforced composites and plastics. And what we want to enable is a time and cost efficient product development using advanced simulation approaches. We are a spin-off company from the Karlsruhe Institute of Technology in Germany, and our aim is to provide tailored collaboration approaches in terms of seminars and consulting, engineering services, as well as the supply of software add-ons for advanced virtual design, as for instance, our add-on for Abaqus, which is called SimuDrape. Through our international network, we try to support our customers from the scratch to the final product. But so much so far on SIMUTENCE itself. This is the outline of my talk today. We're going to focus on composites forming simulation today, and for this I'm going to give a short introduction motivation to the beginning. Then I will introduce composites forming simulation itself, and after that I'm going to introduce our add-on, which is called SimuDrape. And SimuDrape seamlessly plugs into Abaqus, which makes Abaqus applicable to composites forming simulation. And finally, I'll end up my talk with a short summary and conclusion. Let's begin with the motivation and the introduction. First of all, we have to ask ourselves, why do we want to use continuously fiber reinforced composites? And the motivation for this obviously is lightweighting. Why do we want to make light or conduct lightweighting? Lightweighting enables to reduce consumptions and the reduction of emissions. And beyond that, we are also able to achieve a greater performance of our vehicles, for instance, or also our airplanes. And we are also able to increase the payload potential of our mobiles or airplanes at this point. And for this lightweighting, we can use, of course, fiber reinforced composites. This is what we know about this, but we can also show this directly in a so-called Ashby diagram. What we can see in this Ashby diagram is the elasticity modulus over the density. And this gives us a direct insight into how different materials behaves in the context of lightweighting. And we can see in there like the usual metals, as well as continuously fiber reinforced composites. And for this, because we want to achieve at least to get the highest elasticity out of it for the lowest possible density, we can see that fiber reinforced composites behave very well here. So what we can summarize is that continuously fiber reinforced polymers are highly suited and a promising alternative to metals for lightweighting. But what is a fiber reinforced composite, and especially a continuously fiber reinforced composite? What we have to know is that continuously fiber reinforced composites consist of two components. We have on the one side the fibers, which can be woven or unidirectional, and on the other side we have the matrix, which can be either thermoset or thermoplastic. Now we also do have like different type of pre-products for continuously fiber reinforced composites. The pre-product can be on the one side a textile, which is just like a textile as we can see it down here. It can be also a woven fabric or a unidirectional fiber system, and this is usually used in a first draping process and a subsequent infiltration process to achieve our final part. So this is one type of pre-product. On the other side, we can also have pre-impregnated pre-products. This means that we have in combination like directly the fibers in the matrix in the initial state, and these so-called prepregs are then formed and solidified. And such a prepreg we can see down here in this picture. Today in my talk, I'm going to focus on prepregs. And in particular today we are going to talk about thermoplastic prepregs. And for thermoplastic prepregs we have two different types of preproducts. These two pre-products are manufactured in the so-called thermoforming process. The two different pre-products we have here can be either a unidirectional tape or an organosheet. The main difference here is that on the one side, the fibers are aligned as unidirectional fibers, and on the other side, we have a woven fiber structure. And again, today here, or to make a more, let's say, the goal for today. And we are going to talk about thermoplastic UD tapes. Now, having a closer look into how the processing route for thermoplastic UD tapes look like, we can see that we have different material states during thermoforming. It begins with a stripe, which is supplied on a roll. So this is the pre-product which is supplied by the material supplier. This is used in the first step, which is called tape laying process, to place these stripes adjacent to each other and on top of each other to form the particular laminate. This is then used in a subsequent step, the so-called pre-consolidation step, where this blank is heated up well above the melting temperature of our thermoplastic and then cooled down under transversal pressure. And finally, we use this 2D blank in the final step, which is called the thermoforming step itself, which transforms the 2D blank into the 3D part. Having a closer look into this thermoforming step, we can see that first our blank is heated up to make it flexible and formable. Then it's transferred and positioned in the mold. And in the next step, the mold closes, which is usually done displacement controlled. And this in particular forms our 2D blank in our 3D part. Finally, we apply the so-called consolidation pressure, which brings us to the point to solidify and consolidate our part. If we now have a closer look into this forming step, we can see that we are facing different challenges here. On the one side, we can have manufacturing defects. And the main manufacturing defect in thermoforming processes is wrinkling behavior. We can nicely see this here for this surface scan of this partly formed part, that especially above this corner bending here, we have distinct wrinkling behavior. We can analyze this here because what we did here is to stop the forming process for a certain tool gap, and the thermoplastic solidifies and we can check this partly formed part. And based on this, we can nicely investigate how the formability looks like. And in this case, we can nicely see the wrinkling behavior. So this means that on the one side, we are facing manufacturing defects, but on the other side, we also have to know that we are modifying the fiber structure due to the forming. In this case, we can see this here for the fiber orientation. So this is a local CT scan, and the different colors shows nicely how the fiber orientation has changed due to the forming in the area of this corner bending here. Now, knowing that there are different challenges during thermoforming processing or manufacturing of such UD tape laminates, I'd like to have a look into how conventional product development streams look like. So it usually begins with the product design itself. This means that we design our part to design space and certain load requirements and functionalities, ending up with a certain CAD design of our part. This is brought in the next step into the engineering step, where finite element analysis is used to select suitable materials. Important here is that usually no manufacturing effects are considered. So this means that we do not know what is the influence of the manufacturing processes on the final structural behavior of our part. In the next step, it comes to manufacturing piloting and manufacturing of prototypes. These prototypes are then tested, and if the load requirements are fulfilled, it comes to the manufacturing validation and the large volume production. However, we have to know that the later we are facing or observing any challenges during this product development value stream, the higher the costs will be to react on these challenges. And this is why we from SIMUTENCE strongly believe in the digital product development cycle, which has a close interaction between product design, manufacturing validation, and engineering. And this is achieved through advanced simulation approaches, using in particular process simulation to guarantee or to gain the knowledge about our manufacturing process already in very early design stages. And in particular, without manufacturing any real-world demonstrators. This is achieved through a so-called virtual process chain, which predicts, retains, and considers manufacturing effects for simulation. So coming back, this means that we have a design phase and also optimization phase at the beginning. And then we do not directly go into the structural simulation in terms of an engineering step. What we do is to include also the processing simulation, which has the aim to predict the manufacturability of our design. And subsequently, we use the manufacturing effects predicted by process simulation, such as, for instance, the fiber orientation in subsequent simulation steps, which can be first a warpage simulation, which is done to predict the dimensional stability of our part. And then we transfer the information also gained here to the final structural simulation, for instance, also including residual stresses. And based on this, gain the prediction accuracy of our final engineering step, again, which is the structural simulation. And this brings me to the main benefit to thermoforming simulation or composites forming simulation in general. We can say that process simulation and composites forming simulation enables to virtually validate the manufacturability of a certain part without manufacturing any real-world demonstrators. And in addition, we are able to improve the prediction accuracy of subsequent simulation steps. Now I'd like to go more in detail into composites forming simulation itself. And for this, usually I'd like to begin with this schematic illustration here. So what we can see is a tool which is nearly closed, and we have a laminate in between these tools. This laminate consists of several single plies, as we can see it here. So now we have 3 different plies. Now what's happening during the forming of such a laminate can be categorized into so-called interply mechanisms and intraply mechanisms. If we have a closer look into what this means, so for interply mechanisms, we can see that there is a tool ply slip, which is the frictional behavior between the tool and the laminate, as well as we have a ply slip, which is the frictional behavior between the single plies of our stacked laminate. Frictional behavior is in tangential direction. In normal direction for the ply interaction, we also have a tacking or a delamination if the plies are going to separate. Regarding intraply mechanisms, this is usually subcategorized into membrane behavior and bending behavior. Bending behavior, I think this is obvious. Membrane behavior means the tensile behavior in fiber direction, the tensile behavior perpendicular to fiber direction, and especially the shearing behavior along fiber direction. And now what's done to model such process or such a forming process is just to find constitutive equations describing these deformation mechanisms. And this is what we did using Abaqus in combination with subroutines and our add-on SimuDrape. So what we supply through the add-on SimuDrape is basically a holistic modeling approach, including pre-processing, processing itself, and post-processing. Pre-processing means that we have or supply automatized scripts for meshing of the tools and the laminate using Abaqus CAE. And this enables Abaqus to be used for setting up very efficiently our forming simulation approach, which would take us a lot of time if we would do this like manually. Then it comes to the forming analysis itself, and as soon as we have achieved the forming analysis results, we can post-process these results. And this can be on the one side the determination of a tailoring, which enables us which enables a near net shape forming, or the export of manufacturing effects such as the fiber orientation, which then again is used in subsequent simulation steps to gain the prediction accuracy. Regarding the forming analysis itself, we are using Abaqus Explicit, and SimuDrape just supplies advanced contact and material modeling approaches for different types of pre-products. So we are addressing engineering textiles, thermoset preplex, and thermoplastic tapes. And again, thermoplastic tapes, this is the pre-product we are talking about today in detail. Going more into detail how the modeling approach basically works. So for composites forming simulation, we have to know that there are specific requirements on intraply modeling. This results from the fact that we have a very high fiber stiffness and a comparably low bending stiffness. And this yields the point that conventional braid theories are not applicable in composite forming simulation. To circumvent this issue, what's usually done is to model membrane and bending behavior in a decoupled fashion. This is basically not possible using Abaqus built-in approaches, and this is why we are using user subroutines. And we do this in combination with superpositioned elements. So we are using a membrane element, obviously, to model the membrane part, and we are using a Who-Mat subroutine, so a user material subroutine, to model the rate and temperature dependent material behavior. And we are using a shell element to model the bending part. But what we do here is to use a user-defined shell section integration through the Who-Gen subroutine, which enables us to neglect the membrane part of our shell element. And this yields the point that we have a fully decoupled membrane and bending behavior using Abaqus in combination with user subroutines. Now, having a closer look into membrane behavior, I'd like to begin with how membrane behavior is usually characterized. So we are talking again here about a thermoplastic prepreg. So what we have to do is to characterize material behavior at processing conditions. And this means that the thermoplastic has to be fully molten. And for this purpose, we are using a standard rheometer with a thermal chamber. And if we have a look into this thermal chamber, we can see the characterization setup here. And this is just a unidirectional like bar, which is loaded under torsion. And through this torsional load, we introduce longitudinal shear deformation into our specimen. And based on this, we are able to characterize the shear rate and temperature dependent shear behavior like very accurately for this rheometer setup. Now, to extract the material properties from this characterization test, we use a finite element analysis and tweak the parameters in an optimization procedure until we see good agreement between the characterization test and the simulation result. I brought an example for today how this looks like for a PA6 carbon fiber reinforced tape. This is at 250 degrees C, and we can see the result down here. So the dashed lines show us the model prediction, and the solid lines show us the characterization results. What we nicely can see is that we have a distinct rate dependency, which we see in the test and of course also in our model. This can be seen because if we increase the deformation rate, we obtain a higher torsion moment. What we also see is that we have a very good agreement for the lower deformation rates and a less good agreement for the highest deformation rate. This is just due to the fact that we are using a fairly simple rheological model here. So this is a 4 Kelvin approach, which is only capable to model a constant slope between the curves. But what we saw in the past using more complex rheological models, such as a generalized Maxwell approach, is that including this different slope here into or on part level doesn't have a too big effect. And this is why we stick to the simplest approach we can, which is in our case the nonlinear 4 Kelvin approach, which sufficiently captures the rate-dependent material behavior in the molded material state. So we have talked so far about how material behavior looks like in the molded material state. The question now is what's happening if we have a transition from the molded material state to the solid material state. To characterize this, we have again conducted rheometer tests here. Now we are in the small strain regime. We are having a stationary and oscillating load and a constant cooling rate. And what we nicely can see is that there's mostly no increase in mechanical stiffness if we come from a high temperature and go down to 200 degrees C. At this point, something is happening. We have a steep increase in our mechanical stiffness, or steep increase in the torsional moment we are measuring, until we have again a fairly constant increase, for a fairly constant moment. And what's happening here is in particular the recrystallization, which is happening for semi-crystalline thermoplastics. And this can be described by the so-called relative crystallinity. The relative crystallinity alpha is 0 if we have the material in the fully molded material state, and it's 1 if the material has solidified. And the curve you can see here is determined from a DSC measurement, and we can see nicely that there's a very good agreement between the relative crystallinity and this steep increase for the torsional moment we measured in the rheometry test. So this means because the steep increase here is a function of the cooling rate, that our mechanical behavior is not only a function of the temperature itself, it's also a function of the crystallization kinetics. And to include this into our modeling approach, we are evaluating the total stress, which we see, or which is basically like the forming behavior, the forming resistance itself. We are evaluating this for the mold material state as well as for the solid material state. And this is superpositioned through the state variable alpha, which again is the relative crystallinity, which enables us to couple the mechanical response to the crystallization kinetics. And the crystallization kinetics is also described by just the crystallization kinetics model. And based on this, we are predicting the influence of solidification during processing. Again, the models are given down here. So for the mold material state, we have a rheological model. And in the solid material state, it's just a linear elastic model as of today. So this was so far on intra-ply behavior. A remaining part, of course, is the inter-ply behavior, which again is are the tool-ply interfaces and the ply-ply interfaces. What we do here is for the tool-ply interfaces, just to use the built-in contact constitutive equations which Abaqus supplies, because this is just sufficient what we need for the tool-ply interfaces. For the ply-ply interfaces, this changes a bit because what we have to model here is attacking in normal direction and the slipping in tangential direction. And this is not directly possible using Abaqus built-in approaches, and this is why we are using here subroutine, which models in normal direction a cohesive zone, and in tangential direction we have a linear slipping model to account for the pressure and rate dependent slipping. One remaining slide regarding the theoretical background. It's on the thermal behavior. And the thermal behavior, of course, is described by the heat balance equation. This heat balance equation splits into different terms, as we can see down here. And these different terms can also be related to different mechanisms. So we have the so-called intra-ply mechanisms, which of course is the heat capacity. We have the in-plane heat conductivity, and we also do have the latent crystallization heat, because crystallization is an exothermic process, and therefore we need to account for the heat release of the crystallization. And we also have the inter-ply mechanisms. For the inner plies, this means that we are accounting for the out-of-plane heat conductivity, and for the outer plies, we are accounting for, of course, the tool-ply conductivity, because at all the points where we have a tool-ply contact, this is going to be a major heat sink for our plank. And at the free surfaces, we are accounting for convection and radiation. Okay. So much so far on the theoretical background. I'd like now come to some application examples. So what you can see here is a generic geometry. So this was investigated or used to investigate how forming behavior looks like, and also to validate thermoforming simulation. We also do have some Cripper elements here. So these Cripper elements are modeled here using so-called translator elements in Abaqus. And you can see how this looks like during the real processing. And these are just pneumatic cylinders tensioning our plank to improve the forming behavior. So this is a video. We can see how the plank is positioned on the lower tool and how the mold is closing. We can see how the material is drawn in, and also how some wrinkles are evolving to the end, and these are flattened due to the mold closure. Now, of course, the question is, how accurate is the simulation? And in addition, it's important to know, is it really necessary to include temperature effects during processing? And because this is something which is usually neglected in state-of-the-art approaches. So what we can see here is an experimental result in the middle. And on the left, we have an isothermal forming simulation, where we have assumed that we have a constant temperature and homogeneous temperature of 250 degrees C. And on the other side, we have a thermomechanical simulation. And what we can see is that the outer shape of our product is nicely predicted and in a very good agreement to the experimental test. And this is valid for both approaches, like for the isothermal as well as for the thermomechanical approach. If we have a closer look into a partly formed part, we can see that there is some wrinkling behavior, especially around this bigger corner bending here. This is kind of predicted through the isothermal approach, and it's more pronounced predicted for the thermomechanical approach. Having a closer look around this corner bending here, we can see that for the isothermal approach, only some material accumulations are modeled. In contrast, we nicely can see a wrinkle here. This is not like 100% agreement to the experimental test, but at least the conclusion here would be that here's an issue in thermoforming simulation. And this is the main benefit or the main purpose of thermoforming simulation, to see are there any critical points or any critical areas in our part to be manufactured. The reason for that, of course, or for this difference is temperature or thermal behavior, and we can nicely see that locally the blank is distinctively cooling, and this is especially valid for all the wood-like contact interfaces, and we can see that we have a distinct cooling around this corner bending here. What we also saw for this geometry is that we already have a crystallization during forming at this part flanges here, and also to the end of forming where the mold is just closed. Okay, so one remaining example, this is just showing us how we can influence and model the influence of crippers during processing, and we can see how this distinctively is influencing our forming behavior if we apply some tensile loads at the different spots here around this blank. And this can be directly used to influence and improve the prediction, or sorry, to improve the formability of our blank. Another thing we can do using composites forming simulation is a tailoring determination. So it basically enables us to come from this point where we have a lot of scrap around our surplus material around our part or area of interest, and to enable such a near net shape forming as you can see it here. The approach we are pursuing is an iterative approach, which means that we define our target geometry, increase or scale this target geometry to larger geometry, and just to cut a little bit in each step from our plank until we end up with our final tailoring, which again enables us in the net shape forming. Okay, this is all from my side for today. To give a short summary and conclusion. So what we have seen today is that a virtual process chain enables the reduction of costs and time for product development cycles, because we can gain significant knowledge already in early development phases without manufacturing any real and demonstrators. We also saw that composites forming simulation enables or has a high prediction accuracy regarding manufacturing defects. In particular, this was wrinkling behavior. And we also saw that Abaqus basically is highly capable to conduct these simulations, but let's say only in combination with user subroutines, because there are some restrictions based on the built-in techniques. This is something I already said. So we have very high prediction accuracy. What we saw for the generic geometry I've presented today. And through our spin-off company, we try to supply tailored collaboration approaches and also supply this add-on to our customers, which you have seen today. So now I'd like to thank you for your attention. I'll be around the chat for the next hours to answer any questions there might be. And feel free to contact me also, for instance, via LinkedIn. This is a very easy way to communicate. And now I'd like to thank you for your attention.